Cosmic Conundrum, Why We Need String Theory. Welcome, cosmic explorers, to a journey into the deepest mysteries of the universe. For centuries, humanity has gazed at the stars, pondering our existence and the fundamental nature of reality. We've developed incredible theories like Einstein's general relativity, which elegantly describes gravity and the large-scale structure of the cosmos, from the dance of planets to the expansion of the universe itself. It paints a beautiful picture of space-time as a flexible fabric, warped by mass and energy. However, when we try to peer into the incredibly tiny, the subatomic realm, general relativity clashes violently with our other cornerstone theory, quantum mechanics. Quantum mechanics, with its probabilistic nature and strange phenomena like superposition and entanglement, governs the world of particles, electrons, quarks, and photons. It's an incredibly successful theory, forming the basis of all modern technology, from lasers to transistors. But here's the cosmic conundrum. These two pillars of modern physics, both incredibly accurate in their respective domains, are fundamentally incompatible. When you try to combine them, the mathematics breaks down, leading to infinite and nonsensical results. It's like trying to fit a square peg in a round hole, but on a cosmic scale. This incompatibility is the grand challenge of physics, the quest for a theory of everything that can unify all fundamental forces and particles. And this, my friends, is where string theory enters the stage, offering a radical and elegant solution to this profound problem. The quantum quagmire, the particle problem. Let's delve deeper into why combining gravity and quantum mechanics is such a headache. At the heart of the problem lies the concept of a point particle. In quantum field theory, which is the framework for describing subatomic particles, these particles are treated as infinitesimally small, dimensionless points. Imagine trying to describe the interaction between two of these point-like particles, especially when one of them is the graviton, the hypothetical quantum of gravity. When you calculate their interactions at extremely high energies, which is what happens at the quantum scale, the math becomes catastrophic. The probability of these interactions goes to infinity, indicating a fundamental flaw in our understanding. It's like trying to divide by zero. The equations just explode. This isn't a minor hiccup. It's a gaping wound in our understanding of the universe. The very idea of a point particle, while incredibly useful for quantum mechanics in its current form, seems to be the stumbling block when gravity comes into play. General relativity describes gravity as a smooth, continuous curvature of space-time. Quantum mechanics describes everything else in terms of discrete, quantized packets of energy and matter. How do you quantize something as fluid and continuous as space-time itself, especially when the entities interacting with it are supposed to be infinitely small points? This is the quantum quagmire. Physicists have spent decades trying to smooth out these infinities, using various mathematical tricks, but these often feel like temporary patches rather than a fundamental solution. We need a new way to think about the universe's most fundamental constituents, something that can bridge the chasm between the incredibly small and the unimaginably large. The birth of strings. A new fundamental idea. In the late 1960s and early 1970s, a revolutionary idea began to emerge, not as a direct attempt to unify gravity, but as a way to describe the strong nuclear force, which binds protons and neutrons together within atomic nuclei. This idea proposed that the fundamental constituents of the universe weren't point-like particles, but tiny, one-dimensional strings. Imagine these strings as incredibly thin, like cosmic rubber bands, far too small to ever be observed directly with current technology. The groundbreaking insight was that the different ways these strings vibrate, much like the strings on a violin, determine what kind of particle they appear to be. One vibrational mode might correspond to an electron, another to a photon, and yet another to a quark. Instead of a zoo of fundamental particles with seemingly arbitrary properties, string theory suggests that all particles are merely different musical notes played on the same fundamental string. This elegant concept immediately offered a potential solution to the quantum quagmire. Because strings have a tiny but finite length, they smear out the interactions that cause infinities in point particle theories. No longer are we dealing with infinitely small points colliding, but rather tiny loops or segments interacting. This smearing effect fundamentally changes the nature of gravitational interactions at the quantum level, potentially resolving the inconsistencies that plagued earlier attempts at unification. The Graviton song, String Theory and Gravity. Here's where string theory truly shines and offers its most compelling promise. It naturally incorporates gravity. One of the vibrational modes of these fundamental strings, when analyzed mathematically, perfectly matches the properties predicted for the graviton, the hypothetical quantum particle responsible for mediating the gravitational force. This was not an ad hoc addition or a forced fit. Gravity emerges organically and inevitably from the very framework of string theory. Think about it. Our best theory of gravity, general relativity, works perfectly on large scales, but breaks down when we try to quantize it. String theory, developed to describe all fundamental forces, automatically includes a particle with the exact characteristics required to be the carrier of the gravitational force, consistent with quantum mechanics. This is a monumental achievement. It suggests that gravity isn't some separate, aloof force, but just another melody played on the cosmic strings. This intrinsic inclusion of gravity is what makes string theory such a powerful candidate for a theory of everything. It's the first theoretical framework that genuinely aims to unify all four fundamental forces of nature: the strong force, the weak force, electromagnetism, and gravity, within a single, consistent mathematical structure. The graviton, the elusive quantum of gravity, finds its rightful place as a specific vibration of a string, humming its unique tune through the fabric of space-time. Extra dimensions, a hidden reality. Now, prepare for a truly mind-bending aspect of string theory. It requires extra spatial dimensions beyond the three we experience: up, down, left, right, forward, backward, and the one of time. The mathematics of string theory only works consistently in a universe with either 10 or 11 spacetime dimensions, depending on the specific formulation. Wait, you might be thinking, if there are extra dimensions, why don't we see them? This is where the concept of compactified or curled up dimensions comes into play. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but if you get closer, you see that it has a small, curled-up second dimension, its circumference. Similarly, string theory proposes that these extra dimensions are incredibly tiny, curled up into minuscule shapes, far smaller than even the smallest subatomic particles. They are so small that we don't perceive them directly. Our universe's fundamental particles and forces, including light and gravity, are free to move along our familiar three large dimensions, but they are confined to vibrating within these curled-up extra dimensions as well. The precise shape and size of these extra dimensions could determine many of the fundamental constants and properties we observe in our universe, such as the masses of particles and the strengths of forces. It's a truly elegant solution to explain why we only see three large spatial dimensions, while simultaneously providing the necessary mathematical framework for string theory to function. A multiverse of possibilities. The landscape. The idea of compactified extra dimensions, while elegant, opens up another astonishing possibility: a multiverse. The problem is, there are an enormous number of ways these extra dimensions can be curled up, an astronomical number of possible shapes and geometries for these tiny, hidden spaces. Each different configuration of these compactified dimensions would lead to a slightly different set of physical laws, particle masses, and fundamental constants in our observable universe. This vast collection of possibilities is often referred to as the string landscape. Imagine an incredibly vast mountain range, where each peak and valley represents a different possible universe, each governed by its unique set of physical laws determined by the shape of its extra dimensions. Our universe, with its specific laws and constants that allow for the existence of stars, galaxies, and life, would simply be one particular valley in this immense landscape. This concept has profound implications. It suggests that the fine-tuning of our universe, where many physical constants seem perfectly set for life to emerge, might not be an incredible coincidence, but rather a selection effect. If there are countless other universes with different laws, it's not surprising that we find ourselves in one that is conducive to our existence. The string landscape provides a framework for thinking about the origins of our universe's specific properties, moving away from the idea of a single, unique outcome. Superpartners and supersymmetry, a deeper symmetry. Another crucial ingredient in most versions of string theory is a concept called supersymmetry, often abbreviated as SUSY. Supersymmetry proposes a deep and elegant symmetry between two fundamental classes of particles, fermions and bosons. Fermions are matter particles, like electrons and quarks, which have half-integer spin. Bosons are force-carrying particles, like photons and gluons, which have integer spin. Supersymmetry postulates that every fermion in the standard model of particle physics has a corresponding superpartner boson, and every boson has a corresponding superpartner fermion. For example, the superpartner of an electron, a fermion, would be a selectron, a boson, and the superpartner of a photon, a boson, would be a photino, a fermion. If supersymmetry were perfectly realized in our universe, we would have already detected these superpartners, as they would have the same mass as their standard model counterparts. However, since we haven't seen them, physicists believe that if supersymmetry exists, it must be broken at some energy scale. This means that superpartners would be significantly more massive than their standard model counterparts, making them harder to produce and detect in particle accelerators like the Large Hadron Collider. Supersymmetry is incredibly attractive for several reasons. It helps to stabilize the mass of the Higgs boson, resolving a major puzzle in particle physics known as the hierarchy problem. It also provides natural candidates for dark matter, the mysterious substance that makes up about 27% of our universe, but which we cannot directly observe. M-theory, the mother of all strings. As string theory developed, it wasn't just a single theory, but rather a collection of 5 distinct, consistent string theories, each with slightly different properties and dimensions. This raised a new question. If they all describe the universe, how can there be 5? This perplexing situation led to one of the most significant breakthroughs in the 1990s, the realization that these 5 string theories were not independent, but rather different facets or limits of a single, more fundamental theory, tentatively called M-theory. M-theory operates in 11 space-time dimensions, one more than some of the original string theories. The M in M-theory is often said to stand for mystery, membrane, or mother, reflecting its enigmatic and all-encompassing nature. M-theory doesn't just involve one-dimensional strings. It also includes higher-dimensional objects called branes, short for membranes, such as two-branes, surfaces, and even higher-dimensional p-branes. In this view, our entire universe, with its 3 large spatial dimensions, could actually be a giant 3-brane floating within a larger 11-dimensional space-time. This means that particles and forces, except for gravity, might be confined to our brain, while gravity, which is a property of space-time itself, could propagate into the extra dimensions, potentially explaining its apparent weakness compared to other forces. M-theory is still largely theoretical, and its full mathematical structure is not yet completely understood, but it represents the most ambitious attempt to unify all consistent string theories into a single comprehensive framework. Challenges and criticisms. The path forward. Despite its elegance and profound theoretical insights, string theory faces significant challenges and criticisms. The most prominent challenge is the lack of direct experimental evidence. Because strings and extra dimensions are predicted to be incredibly small, far beyond the reach of current particle accelerators, directly verifying string theory is extremely difficult. This has led some critics to argue that string theory might not be a scientific theory in the traditional sense, as it currently lacks falsifiability. Another challenge is the string landscape problem we discussed earlier. While it provides a potential explanation for the universe's fine-tuning, the enormous number of possible vacua, different configurations of the extra dimensions, means that string theory doesn't uniquely predict our universe's properties. It offers a framework, but doesn't pinpoint a single outcome, leading to questions about its predictive power. There are also ongoing debates within the physics community about the mathematical completeness of string theory, particularly M-theory, which is still not fully formulated. Some physicists also express concerns about the theory's mathematical complexity, arguing that it might be an overly intricate solution. However, proponents of string theory emphasize its remarkable consistency, its natural inclusion of gravity, and its ability to resolve deep theoretical inconsistencies in quantum mechanics and general relativity. They believe that even without direct experimental verification, the mathematical beauty and coherence of string theory make it a compelling candidate for a deeper understanding of reality. The future of string theory, a glimpse into the unknown. So, what does the future hold for string theory? The pursuit of a theory of everything is one of humanity's grandest scientific endeavors, and string theory remains at the forefront of this quest. While direct experimental verification of strings and extra dimensions is currently beyond our technological reach, physicists are exploring indirect ways to test the theory. One promising avenue is searching for evidence of supersymmetry at the Large Hadron Collider. If superpartner particles are discovered, it would provide strong support for one of string theory's key predictions. Another area of research involves looking for subtle gravitational effects that might arise from extra dimensions, or trying to find unique cosmological signatures from the early universe that could be explained by string theory. Even without definitive experimental proof, string theory continues to be an incredibly fertile ground for theoretical physics. It has led to profound insights in mathematics, quantum field theory, and even black hole physics. Many of the mathematical tools and concepts developed for string theory have found applications in other areas of science. The journey to understand the fundamental nature of reality is a long and arduous one, filled with twists and turns. String theory, with its audacious proposal of a universe woven from vibrating strings, represents a monumental leap in our imagination and our quest to unify the cosmos. It pushes the boundaries of human thought, inviting us to consider a reality far richer and more intricate than we currently perceive. Whether it turns out to be the ultimate theory of everything or a crucial stepping stone to an even deeper understanding, string theory has already profoundly reshaped our vision of the universe.